this lecture, we will look into how does the second rank tensor transforms when we do a transformation of axes. Now, let me just quickly review what we had done in the last lecture and then continue on from that point of view. So, what we had seen in the last lecture was that there is a cause vector P and there is an effect vector Qi, or we can also call P as some kind of a generalized force and Q as some kind of a generalized displacement. Q and P are related through the tensor T. Basically, this is my second rank property tensor. Now, it could be electrical conductivity, it could be thermal conductivity, many other properties. Also, this is written in tensor notation. The same thing could be written in the form of a matrix here, where Q and P have 3 components and tensor T has 9 components: T11, T12, T13, T21, T22, T23, T31, T32, T33, and we have the cause vector with 3 components P1, P2 and P3. In an abbreviated form, one will write the 2 vectors and the matrices as in the form of matrices like this. Now, in order to figure out how the tensor transforms if I transform my axes, we have to look at how a vector transforms, and the axes that I am going to talk about we will be using throughout would be orthogonal axes x1, x2, x3, all the 3 axes being perpendicular to each other, or Cartesian. Basically, we are working in Cartesian space. So, if I have, how do I represent a vector? x1, x2, x3 are the 3 axes, and let us say there is a vector P which can be represented by 3 components: component along x, component along x1, component along x2 and a component along x3. So, I have component P1 along x1, P2 along x2 and P3 along x3. So, my vector P is written like this: P1, P2, P3. Now, we want to figure out what these components would be in a transformed axis system. So, going from x1, x2, x3 to another set of orthogonal axes x1 prime, x2 prime and x3 prime. x1, x2 and x3, and then a new axis system, I will call that as x1 prime, x2 prime and x3 prime. How are these related to the old axes x1, x2, x3 is in the following way. Let us say, how do I represent the direction x1 prime with respect to the old axes x1, x2, x3? Could be through 3 angles. So, I have an angle x1 prime between x1 prime and x1, I denote it as x1 prime x1 in this way. Similarly, I have an angle between x1 prime and x2, x1 prime, x2, and an angle between x1 prime and x3 Now, in this new axis system, let us say I have a vector p whose components are p1, p2, p3 along x1, x2, x3. In the new axis x1 prime, x2 prime, x3 prime, the components for the vector p would be p1 prime, p2 prime, p3 prime. So, we want to find out now what are these three components. After all, the vector still is the same, whether it is referred to the old axis or the new axis, except its components will have to be changed with respect to the axes that we have chosen. So, looking at the first component p1 prime, this would be equal to very clearly sum of the components of p1, p2, p3 along x1 prime. Now, what are the components individually? What is a component of p1 along x1 prime? It would be p1 times the cosine of the angle that the x1 prime axis makes with the axis x1. So, in the sum, the first term would be p1 cosine of angle x1 prime with x1. Similarly, the second term would be p2 times the cosine of x1 prime with x2 plus p3, the third term cosine p3 times the cosine of x1 prime with x3. Let me call all of these cosine terms. Let me call the first term cosine of x1 prime x1 as a11, cosine of x1 prime with x2 as a12, cosine of x1 prime with x3 as a13. And therefore, p1 prime becomes a11 p1 plus a12 p2 plus a13 p3. Now, what are these a1, a12, a13? They are simply called as direction cosines of the vector x1 prime, and these direction cosines are with respect to the axes x1, x2 and x3. Similarly, one would be able to write down now the component for p2 prime as a21. Now, in this case a21 is the angle cosine of the angle made by the x2 prime axis with the x1 axis. So, this would be a21 p1. I have taken the component of p1 along the x2 prime axis this time. Similarly, component of p2 along the x2 prime axis would be a22 p2 plus a23 p3. In the same fashion, the third component p3 prime becomes a31 p1 plus a32 p2 plus a33 p3. So, here the first index, which is 3, is the x3 prime axis, and the cosine of the angle that the x3 prime axis makes with the axis x1. So, A31, and similarly A32 is the cosine of the angle made by the x3 prime axis with the x2 axis, and cosine of the angle made by the x3 prime axis with the axis x3. And this fashion we have got all the three components of the vector p in the new axis system x1 prime, x2 prime and x3 prime. Now, in tensor notation, which we have discussed in detail in the last lecture, all these sets of equations can be written as Pi prime equals Aij Pj, recalling that j here is the dummy index, and therefore, this implies a summation of over j equals 1 to 3, and I is the free index which also goes from 1 to 3. So, we get all the three equations in this abbreviated tensor notation. In matrix form, also I can write this equation as follows. So, P prime here represents essentially the transformed vector with its transformed components. So, A11, A12, A13. So, I am writing the direction cosine matrix A21, A22, A23, A31, A32, A33, and then I have the vector in the old axis system as P1, P2, P3, or very briefly this could be written as P prime equals to, and let me call the direction cosine matrix with the letter capital A multiplying into the vector P. Now, similarly, for vector q now, how that transforms in the same way. Similarly, for vector q, I could write q prime equals Aij Qj in the same fashion as out here. Let me just recopy these equations. So, my vector P prime is Aij into Pj, the vector Qi prime, the direction cosine matrix, the Aij component times Qj. Then I can also write the reverse transformation. The reverse transformation could be written as P1. So, I want to get back to the old axis from the new axis, that is the reverse transformation. So, P1 would be A11 P1 prime plus A21 and not A12, A21 times P2 prime plus A31 P3 prime. So, here for example, A21. So, A21 is the cosine of the angle made by the x2 axis with the x1 prime axis. So, we get this reverse transformation. P2 equals A12 P1 prime plus A22 P2 prime plus A32 P3 prime. Similarly, we get back the old component P3 by A13 P1 prime plus A23 P2 prime plus A33 P3 prime. So, in tensor notation, this will become Pi equals Aji P prime j, and in the form of a matrix, this would be P times the matrix A, but this time this is Aji. Therefore, this is the transpose of the matrix A times P. Similarly, for Q, I have Qi equals Aji Qj prime, and in matrix form we get Q equals transpose of A superscript T times Q prime, and this will also be P prime. So, now we know how to transform the vectors P and Q. Now, I need to find out how does my tensor property itself transform. So, essentially what we are trying to say is, in the old axis system, I can write Qi as Tij Pj. Now, when I have transformed, so after transformation, Qi becomes Qi prime, Pj becomes Pj prime, and the two are related through this transformed tensor Tij prime. So, now I have to find out how does this transformation takes place, that is Tij transforms to T prime Ij. So, it's fairly easy to do this. Let us see how this can be done. Let me write Qi prime. Let me write this Qi prime as Ai, and instead of using the index j, I am going to use the index m. So, it becomes Qi prime equals Aim Qm. Now, Aim Qm, I mean, we have not changed the equation in any way. I have just changed the dummy index j to the dummy index m. So, let me begin here. Qi prime equals Aim Qm. Now, let us substitute for Qm. Now, Qm, let me look at the reverse transform and change the subscript I to subscript m. So, Qm can be written as, I did not write one equation, let me write that, the reverse transformation, not the reverse transformation, rather I had this Qi equals Tij Pj. Now, this can be changed to, instead of writing it as Qi, let me change the index I here to m. So, Qm can be written as Tij Pm. And therefore, I can write Qi prime and substituting Qm on the right hand side, Qi prime equals Aim, and I have to change this subscript also in the vector. So, actually I made a error here. Let me write this as Qm equals, instead of Ij, I write Mn. So, I can write Qm equals Tmn Pn. So, I have changed all the subscripts, subscript I is changed to M, subscript j is changed to n, and now I can write Qi prime equals Aim, and I am substituting for Qm. So, this will become Tmn Pn. Now, just another small change is, now we will substitute for Pn. And how do I substitute for Pn? Well, let us look for the change out here. Change the look at the reverse transformation. So, let us look here. P, change the subscript I to n. So, Pn is written as A j n Pn prime. So, out here this is not P prime j here. Okay. So, we are coming out here and substituting into this equation. So, Qi prime equals Aim Tmn, and now for Pn I substitute Ajn Pj prime. So, yeah, so this is the final relation that I wanted. Now, here let us compare, comparing this equation with this particular equation out here. We will see that the combination of these three terms Aim, Tmn, Jn is nothing but T prime Ij. M and n are dummy indices, they will be, so over summation they will disappear, and you will be left with the transformed tensor T prime Ij. Now, this transformed tensor T prime Ij, now the individual quantities, if you look in this tensor notation, they are all scalar quantities. So, therefore, I can always rearrange these terms, and I can write the final relation for just T prime Ij as Aim Ajn Tmn. So, these set of equations will transform the tensor when we transform the coordinate axes. In matrix form, the transformation would look something like this: A11, A12, A13, A21, A22, A23, A31, A32, A33, this matrix multiplying into the untransformed or the tensor in the old axis as T11, T12, T13, T21, T22, T23, T31, T32, T33, and so basically I have taken this term, I have taken this term, now I have to take this term. This you will notice is a transpose of the direction cosine matrix. So, it will become A11, take the rows into columns, A12, A13, A21, A22, A23, A31, A32, A33. So, this is the matrix form of this, and here we cannot do this rearrangement, because these are matrices and not scalar quantities. I can refer to this first matrix as A, the tensor as T, and this would be the transpose of A. Hence, the final result in matrix form can simply be written as A into T into A transpose. So, you can compare these two results. This is written in tensor notation and this is written in matrix form. Now, before I close this lecture, I just want to talk about a little bit about the properties of the A matrix or the direction cosine matrix. Now, this direction cosine matrix, let us start with multiplying the direction cosine matrix with its transpose. So, A multiplying into A transpose. So, that is the first row of the matrix A, second row A21, A22, A23, A31, A32, A33, and its transpose. So, A11, A21, A31, A, this second term would be second row starting with A12, A22, A32, then A13, A23, A33. If you multiply, let us just multiply a couple of terms. So, multiplying the first row into the first column will give me the first term in the new matrix, and as you can very clearly see that this is going to be A11 square plus A12 square plus A13 square. This is the first term in this matrix. Second term, again multiply the first row into the second column of the transpose. So, this will become A11, A21 plus A12, A22 plus A13, A23. Then there will be some term out here. Similarly, we can get terms at, so you can get all the 9 terms, but just let me just consider these 2 terms. So, let me consider this term, let me call it as 1. So, term 1, what is term 1? Term 1 is nothing but the sum of the squares of the direction cosine for the vector x1 prime, and sum of the squares of the direction cosines for any given vector is actually nothing but unity 1. So, therefore, A11 square plus A12 square plus A13 square equals 1. So, that takes care of this. Let us look at term 2 now. I will call this as term 2. Now, what is this? Well, if you think about it a bit, I can write the vectors x1 prime as a11 x1 plus a12 x2 plus a13 x3 and the vector x2 prime as a21 x1 plus a22 x2 plus a23 x3. If I take the dot product x1 prime dot x2 prime, it is nothing but the term 2 that we have got. Now, what is the dot product of this? Well, we are talking about, we said that we will be working with orthogonal axes, x1, x2, x3 are orthogonal. Similarly, x1 prime, x2 prime, x3 prime also orthogonal. So, dot product of two vectors at 90 degrees to each other would simply be 0, and hence the term 2 is simply 0. So, the final result that we get is that A transpose, and you can verify this yourself by looking at the other terms, would simply be 1 0 0 0 1 0 0 0 1, and this is nothing but the identity matrix which we denote it as I. Now, following with this, if I take the determinant of A into A transpose, this would be nothing but determinant of the identity matrix, and the determinant of the identity matrix is simply unity or 1. Now, determinant of product of two matrices can be written as a product of their individual determinants. So, I can write determinant of A transpose can be written as determinant of A into determinant of A transpose, and that is equal to 1. Now, determinant of A transpose of a matrix is the same as the determinant of the matrix itself. Therefore, this is nothing but determinant of A, and hence determinant of A multiplied by determinant of A again equals 1. From here, it is very clear that determinant of A can be plus or minus 1. Now, whenever there is a axis transformation in which a right handed axis go to a left handed axis, you will get a minus 1. If it goes from right handed to right handed, you would get a plus 1. Thank you.